Hi, in this video I'll explain the working principle of a barometer and how it's used to measure atmospheric pressure. So first of all, take a vessel and fill some mercury in it to a certain depth, so you have a pool of mercury floating there. Take a test tube or tube full of mercury to the brim, invert it and dip it below the level of mercury in the vessel and release your finger. What you will notice is that the mercury in the tube drops down to a particular level and it stays right there. What's happening here is the atmospheric pressure, which is acting in all directions, is also pressing down on the pool of mercury. And since above the mercury in the tube there is just vacuum, because the mercury just dropped its level down and we didn't fill any air into that place, so the atmospheric pressure finds no opposition from a pressure point of view, and therefore the mercury stabilizes at that level that you see in the image. And the question is that if there is no opposition to the atmospheric pressure and there is only vacuum on top of that meniscus, then why doesn't the mercury keep on rising further? The reason is that all this pressure finally has to translate to a force. So the force that keeps up the mercury rising to that particular level is opposed by the weight, which is also a force, of the mercury column itself that is standing there. And these two forces, when they balance, they create that equilibrium height of that mercury column in that tube. The height of that mercury column is 760 millimeters of mercury column, and that's defined as the atmospheric pressure, or the maximum height to which atmosphere can push that mercury up that tube. Please do this measurement at the top of that meniscus, and that's the rule for any convex meniscus. And if it's a concave meniscus like water, the reading has to be taken at the bottom of the concave meniscus. Now let's look at the balancing act of the atmospheric pressure. Pressure is force by area, and the force above the mercury meniscus is zero because there is vacuum, as we said above that. The force due to the weight of that mercury column that's being held up by the atmospheric pressure, W is equal to mg, and mass is density into volume. Volume is area of cross section of the tube into the height, and here height is the most important thing. So multiply rho by pi r squared, which r is the radius of the tube, height is h, and then we have g. And therefore the pressure of atmosphere is force by area, there's weight by area, and pi r squared will cancel out and you will get rho into h into g, where h is the great height of that mercury column. Now we plug in the values, and values for density of mercury. Height, we know it's always 760 millimeters at sea level. Of course, if we go on a mountain or a very tall snow-capped hill, then we will find it to be less than 0.76 meters. Multiplied by g, the famous 9.81 meters per second square, and you will get some units. The units may look strange, so we have to convert it into newtons per meter square, which is the correct unit for pressure. So there is a jugglery there in terms of dimensions, which I have shown, multiply and divide by meters and so on till you get newtons per meter square, and that's pascals. So you get atmospheric pressure as 1.01 10 to the power 5 pascals, and that's written as 1 atmosphere. I hope this presentation was useful for you. Thank you and have a great day.